This is Precalculus section 4.5 notes. We've arrived at the last section of chapter 4, our exponents and logs section or chapter, and this section is our application section. I think it's a pretty easy section. You have some equations that you're given to work with, so basically it's kind of a plug and chug. You take the information from the problem and you plug it in and you solve for what you don't know. Okay, so we're going to begin with our exponential growth model. N of t is equal to n naught times e to the rt. Okay, so n of t, that's going to be the population at time t, so the population after a certain period of time. R is our relative rate of growth, which is going to be expressed as a proportion of the population. Okay, we'll talk about that. N naught is the initial size of the population, and t is the time period. Let's take a look at example 1. Says the initial bacterium count in a culture is 500. So we know that's our N naught. I'm going to go ahead and write that down. A biologist makes a sample count of bacteria in the culture and finds that the relative rate of growth is 40% per hour. So 40% of the population per hour. So again, if R is 40%, then when we plug that into our equation, we need to change that to a decimal. So that will be 0.4. So our first job is to just write a function that models the number of bacteria after t hours. So n of t is going to be equal to our initial population, which is 500, times e is just itself, to the rt, so 0.4 t. Part B says, what is the estimated count after 10 hours? So basically we just have to plug 10 in for t. N of 10 is going to be equal to 500 times e to the 0.4 times 10. You grab your calculator, you type that in, you should get 27,299. It's 0.08, but we're just going to leave it as 27,299 because we're counting the number of bacteria, so we're going to round to the nearest whole bacteria. Our second example says a certain breed of rabbit was introduced onto a small island about 8 years ago. The current rabbit population on the island is estimated to be 4,100, with a relative growth rate of 55% per year. So the question is, what was the initial size of the rabbit population? So this time we're going to be solving for that n naught in the equation. Well, we know that our model looks like this. N of t is equal to n naught times e to the rt power. So the current population is 4,100. We don't know n naught. We're trying to solve for it. Okay. Our relative growth rate is 55% per year. Okay, so we're going to have 0.55. And if we want to know the initial size, remember, it's been 8 years. So our time period here is 8 years. So we go ahead and we type e to the 0.55 times 8 power first, right? So that's going to give us 4,100 equals n naught. And actually, I just did the exponent. I did 0.55 times 8. That gave me 4.4 as my exponent. Okay, so now I can evaluate e to the 4.4 power. So that gives me 4,100 equals n naught times e to the 4.4 is 81.451. And then, of course, the last step is just going to be to divide by 81.451. So I find out that n naught is equal to 50.3, which is, we'll just do a squiggle equal sign, about 50 rabbits. So that was our initial population, okay? We need that for part B because part B is asking us to estimate the population after 12 years. That sounds goofy. After 12 years from now, that's kind of a typo. So after 12 years, estimate the population after 12 years. All right, so our equation now, we're looking at what is what is n of 12? Well, it's going to be equal to our initial population, which we just found was 50 rabbits, times e to the, still growing at 55%, and we want to know what's that population going to be after 12 years. And then you just grab your calculator and you type this in. 50 times e to the 0.55 times 12 power. Make sure you're typing that in correctly. And we find out that after 12 years, the population is 36,754.76. So we're going to round to the nearest whole rabbit. 36,755 rabbits. Whew. That's a lot of rabbits. The second formula that we're going to learn how to use in this section is the radioactive decay formula. Now, what you need to know about this formula is when you look at it, the formula is m naught, okay, well, that's our initial mass, times e to the negative r times t, negative r times t. And what's important here is that r, the rate of decay, is natural log 2 divided by h, where h is the half-life of whatever the element is that we're talking about. So our r value isn't going to be given straightforward. We're going to have to find it with the information that was given to us in the problem. So if we take a look at example 3, it says potassium 210 has a half-life of 140 days. So that's my H, 140 days. Okay. Suppose a sample of this substance has a mass of 300 milligrams. So that's going to be our m naught. So now we have to figure out our R value. It's simple. It's just natural log of 2 divided by our H, our half-life, which is 140. So that gives us a very tiny number, 0.004951. And now it's just a matter of plugging everything into the function. So our function is going to be our mass after time t is going to be equal to our initial mass, 300, times e to the negative 8, or negative r, which is negative 0.004951 times t. Then part B says, find the mass remaining after 1 year. So 1 year, remember our t here is in days, because our half-life was given as 140 days. So that's important, okay? You might want to underline that, circle it something in the problem so you remember that your time here is in days, okay? So if we want to find the mass after 1 year, then that means that our time period is going to be 365 days. So that's what we're going to be plugging in for our t value, okay? So this is going to look like m of 365 is going to be equal to 300 times our e to the negative 0.004951 times 365. And then you grab your calculator and you type that in and you get 49.24 grams. So we're starting with milligrams, milligrams. We're starting with 300 milligrams, and after a year, we're going to be down to 49.24 milligrams. Okay, unfortunately, my part C here is cut off, so I'm just going to add a page. How long will it take for the sample to decay to a mass of 200 milligrams? All right, well, again, we're solving for time. T, the variable, is in the exponent. Okay, if we want to know how long it'll take to get to 200 grams, remember, that's going to be our mass remaining, which in this problem is our m of t, right? So 200 is going to be equal to our starting amount, which is 300, times e to the negative 0.004951 times t, because we are trying to figure out how long it's going to take for our 300 grams milligrams to turn in to 200 milligrams. We've done problems similar to this before. Our Mr. Moneybags problem in the last section, the math was just like this. We know we're going to have to change form, but before we do that, we're going to need to get the exponential term alone. So our first step is going to be to divide by 300. 200 divided by 300 gives me 2/3. So 2/3 is going to be equal to e to the negative 0.004951 t. Okay, now we're going to change form. The base of the exponent becomes the base of the log. Since our base is e, then it's going to be a log base e, which is an ln. So we have ln of 2/3 is equal to our exponent, which is negative 0.004951 times t. Then we grab our calculator and we evaluate ln of 2/3, which is negative 0.40547, and that's equal to negative 0.004951 t. Of course, the last step is just going to be to divide. So we divide by negative 0.004951 on both sides on the calculator, and we get t equals 81.91. And remember, our time, our unit of time for this problem is days. So there's the answer to our question.